All right, welcome back to ECE484. This is our third lecture for fall 2021. Okay, so hopefully everything is going well with the intro lab and everyone's been able to sort out their schedules and so on. Lab 1 starts officially on the 16th, I believe. And so, please keep an eye on Learn for all scheduling issues associated with the lab. Okay, so what did we do in lecture number 2? We finished our introductory card example. It was a very trivial example, it was a simple example, but it gave you some of the ideas that we're going to cover in this course, right? There was some elements of continuous control design, sampling, converting discrete signals back to analog signals, and so on. Okay? We then talked about sort of the different paradigms for control systems, right? So there's continuous time, which you've seen. Discrete time control systems, which you probably haven't studied formally, but very similar conceptually to what you know from continuous time. And then kind of the new aspect, or the interesting aspect of this course, which is the sample data control system, which has a mix of both continuous and discrete time systems, right? So what modern day parlance you might call a cyber physical system. Okay. And then we started talking about the design approaches that we're going to cover in this course for sample data systems. Okay, and the two, really didn't talk about the second one, but I'll mention it now. The two are emulation and direct design. So emulation is, if you think back to our introductory example, where you take the point of view of the cart. And from the point of view of the cart, everything looks continuous, right? It's a completely continuous time system. And so we ignore the analog to digital converter and the digital to analog converter, so just completely ignore them. Don't even treat them as if they weren't there. Then you have then you're in the continuous paradigm, and you design CFS for the continuous time problem. Okay, so you've learned some approaches to continuous time control design. In this course, we will learn new ones, but in principle, that's the idea. And then you will approximate the continuous time controller to generate the digital controller, which again, underneath the transfer function is a difference equation. So you're generating this recursive rule for updating your control signal. Okay? And that approach, the emulation approach, works well with fast sampling. And the rule of thumb we gave last class, and that we'll talk about, of course, in more detail, is about 5 times. The sampling rate should be about 5 times in terms of frequency, the closed loop bandwidth of the continuous time system. Okay, the other kind of approach is called direct design. And the idea here is that you first discretize the plant model, right? So instead of working with P of S, you work with P sub D of Z, right? So a discrete plant model. And then you treat the sample data system, which is a mix of continuous and discrete, you treat it as a purely discrete time system, okay? At that point, you design D of Z for the discretized plant. And the nice thing about direct design is that it can handle slow sampling, right? So if you have slow sampling, you can still design controllers that work. And it provides performance guarantees at the sampling instance, right? So what we're going to see is there's no approximations involved. And so we get good performance, at least at the sampling instance. The disadvantage is that the analysis can be a bit tricky, as we'll see as we go through. And it tends to ignore the intersample behavior. So while you can get good performance at the sampling points, what's happening in between, you can't really say much. Okay? And that will sort of be the last part of the course. So, emulation we'll see relatively early, chapter 4. Direct design is sort of very much the second half of the course. Okay. So again, if you have any questions, please feel free to use the chat. I'm happy to answer. Okay, so the last thing we want to do here in chapter 1 is, basically come up with a model for our analog to digital converter and our digital to analog converter. Okay, so last thing we want to talk about is models for ADC and DAC. Right, so these are kind of complicated equipment. And so we want to have a relatively simple model for these guys that we can use when we go to do our design and our analysis. Okay, so let's start with the ADC. Oh, by the way, this is also covered in section 4.2 of the notes, but it's very brief, so we'll do it here. Okay, so for the analog to digital converter, the picture you should have in mind is that you send a continuous time signal. Oops. You send a continuous time signal of this form through your ADC. And that produces, again, a discrete time signal, which we draw with dashed lines. Okay, and so for this particular example that I've drawn, it might look something like that. Okay. Now, for a real analog to digital converter, of course, things aren't so nice, right? So what will happen, of course, is that the samples, they won't be exactly at the sampling period. There'll be some jitter in the clock. So the samples aren't exactly at 0t, 2t, etc. Okay? So that's the first kind of real reality of the situation when it comes to an ADC. The other reality is that those values, where the dots are, the lollipops are, they're going to be quantized, right? So if you've ever looked at the data sheet for an ADC, they'll tell you it's 12-bit, 16-bit, how many bits your analog to digital converter has. And so what that means is that you have finite precision. And so over here on the kind of the horizontal axis, the values are quantized. Okay, and so a simple kind of mathematical model for this sort of system, an idealization, is the following, and this is kind of the way we'll treat this ADC in this course. An idealization of this ADC is the following block diagram, where you replace the ADC with kind of two blocks. The first is what we'll always indicate with an S, will be our ideal sampler. And the second block is the quantizer. Okay. So in this picture, what do we have? S is the ideal sampler. Okay, and so what it does is it just samples the incoming continuous time signal exactly at the sampling instance. So i.e., if its input is y of t, right? Because remember, we are reading the output of our plant y through a sensor, and that's producing a discrete value. So if its input to this sampler is y of t, then the output is exactly what you would expect from an ideal sampler. Okay. On the other hand, the quantizer it's the nonlinearity in the ADC is the quantizer. And so if you were to draw the graph of the quantizer, where of course this is the input to Q, and this is the output, it looks like a staircase. So it'll look something like this. The idea being here that, 0, of course, will be mapped to 0 in the quantizer, but so will things near 0, depending on the finite precision. Okay? And then you'll get this discrete jump when you get to the next least significant bit, and so on. Okay, so the quantizer is a nonlinear system. Okay, we will talk about nonlinear systems in chapter 5, I believe. But for the most part, we're going to ignore the quantization effects. Okay, so long story short, when we talk about analog digital conversion in this course, we will talk about an ideal sampler. We will treat the ADC as a sampler, just the S block. Okay? Okay, we want to do the same sort of thing for the digital to analog converter. So for the DAC, okay, so the DAC does the opposite of, as we saw last week. Okay, so it's going to take a discrete time signal and produce a continuous time signal. Okay, so in this picture, let's draw, say, something like this. Okay, so when you run this discrete time signal through the digital to analog converter, you know, it's a circuit, right? It's still at the low level, it's a circuit. So what it's going to do, it's going to look something like this, right? So there'll be, when the value jumps, there'll be a little transient that shows up, right? So you'll see there'll be a little bit of rise time, and there might be a little, I'm exaggerating, of course, but there'll be a little waveform that shows up there. And similarly every time. Et cetera, right? So there'll be some jitter and some, you know, it's an electrical circuit. Okay, and so again, this won't be exactly at t, 2t, et cetera, et cetera. As I've mentioned over here, the jumps won't be instantaneous, so it takes time to jump. In quotations. And furthermore, there's a maximum value that a DAC can put out, right? You can't put arbitrarily large continuous time signals out, right? So there's a max min. Okay. And so, you know, there's all these kind of effects that you know, if you really wanted to model the DAC correctly, you'd have to take into account. For the purpose of control, we're using feedback, so there is some robustness inherently in our designs, so we're going to use a simplified model of the DAC. But let's see. So again, an idealization. Would be the following. And again, I'll explain what these blocks are. So we have this H block, which is going to be our zero order hold, and then the saturation block, which is going to model the max-min values of the DAC. So where H is called the zero order hold. Okay. There are other types of holds, so first order, second order, generalized holds. This is kind of the simplest one, zero order hold. And what does it do? It's what we saw last class, i.e. if the input is UK, discrete time signal, the output is U of t equals UK between the sample periods. Right, so the value is just held constant over one sample period. Okay, the saturator, so sat, is a saturator, and it is also, like the quantizer, it's also a nonlinear block. And what it looks like is that, sort of like what you think of as an op-amp, right? The way an op-amp model would look like. So you have this linear region where the input is equal to the output, but then at a certain point they get capped off because you've reached the largest possible value that your DAC can put out. Similarly, you've reached the smallest possible value that your DAC can put out. Okay, and so of course everything is linear in here. It looks good. We can use our linear system tools. But once you get here, you get to the nonlinear region, and it becomes trickier to analyze. And so, similar comment to the quantizer, the saturator is a nonlinear system. And from the point of view of the DAC, we're going to ignore it, okay? And for the DAC, we ignore it. Okay. Now in the lab, there's another saturator that comes up, and that's from the amplifier, right? You're going to send a command from your digital to analog converter to an amplifier that was going to drive the motor, and that amplifier has this saturator block at the end. And so the strategy in the lab is going to be essentially just make sure you're always working in the linear regime. Try not to get over here where there are these nonlinear effects. Okay. So all that is to say that from now on, the sample block S and the hold block H will play the role of ADC and DAC respectively. So from now on, S and H will play the role, play the roles of ADC and DAC. Okay? And we're also going to assume that they're synchronized by a common clock. Okay? So that's kind of a standing kind of simplification that we're going to make throughout this course, and it's reasonable. It's kind of a standard thing that one would do. Okay, so that's basically it for chapter 1. I just want to make a small provision here to talk about notation that I'm going to use that will come up in this course. So very briefly, for the complex plane, we're going to label different parts of the complex plane using different symbols. So the part of the complex plane where you have positive real part, we're going to call C+. The part where you have negative real part, we're going to call C-. And the imaginary axis, sometimes I will call J times the real numbers. Okay, J for the square root of -1. Okay. In signals and systems, the symbol U is used for the step input, but U, of course, in control systems is traditionally the input to the plant, and so we're going to use the symbol 1 of t for the step input. Okay, so as our unit step. And in discrete time, it'll be similar. So this is the unit step. Okay, so 1 of t and 1 of k to indicate the step. Delta of t will be the impulse function, so the continuous time impulse. Okay, and delta of k will be the discrete time impulse. Right, so it equals 1 when k is equal to 0 and 0 everywhere else. A few other things. Script L is what I'll use for Laplace transform. Okay, and script Z is going to be the Z transform of f of k. All right. Lastly, when I write the symbol I will typically be talking about an identity matrix. Okay, so this is sort of basic notation that we're going to use throughout this course, and so keep that in mind as we go through. Okay, so that completes chapter 1. We're going to talk about chapter 2. And chapter 2 is a review. Okay, so it's going to be a little bit quick. We're going to quickly go over some of the stuff that I expect you to have seen before. I know some of you maybe haven't taken a control course for whatever reason. And so for those people, you might have to review this material a little bit further. Certainly feel free to ask questions as we go through. All right, chapter 2. Review of signals, systems, and analog control. Sorry if my handwriting is a bit worse today. Technical issues forcing me to write this in a slightly different way. Okay, 2.1 you can read on your own. 2.2 transfer functions. Okay, if and only if you have a linear time invariant system, that system has a transfer function. So, what's the picture? Input u of t, output y of t. The block is linear time invariant. Okay. And what do you do to get the transfer function? If I give you a black box and I say find the transfer function, I don't tell you anything about the blocks. I just tell you that it's a linear time invariant system contained inside the box. What do? Well, you pick any input you want, any waveform, u of t, you apply it, you measure the output, y of t, take the Laplace transform of both those signals, and that ratio is the transfer function. So, the transfer function of this system is the ratio y of s over u of s, where all LTs are taken with 0 initial conditions. So what does that mean in terms of what I said before with the black box? I give you that black box. What you do is you let it sit for a while, make sure everything is at rest, nothing is happening with the black box. You apply your input, measure your output, take that ratio, transfer function. Okay, so you may ask yourself, why can't I do that with any system? I give you a black box, but I don't tell you that it's linear time invariant. Couldn't I do the same thing? Couldn't I just wait for it to relax, apply an input, measure the output, and take the ratio of those transfer functions? Well, you could do that, of course. The problem is that for a time-varying system or a nonlinear system, the ratio will depend on the input. And so it's not a useful model for if it's not time invariant, linear time invariant. So you could try this. So you could try to apply this definition to a nonlinear or time-varying system. But the problem would be that different I/O pairs so the pair UY would yield different ratios. Right? And that's the beauty of LTI systems, right? That input-output description can be abbreviated completely. I don't have to keep a list of all input-output pairs to model a linear time invariant system. I just need one ratio. That's the beauty of them. That's the reason that you study them so much in undergrad. Okay, example. So I remind you that when you see those numbers in an example, it means that it's an example which is already in the notes. So it's not kind of distinct to the lecture. Okay, so DC motor you're going to see in the lab a lot, but I remind you, I won't go through very detailed modeling of it. I just want to get the transfer function of it. But the picture you typically have in mind is something like this. Okay, so there's like an electrical part to the DC motor, and then there's the mechanical part, which I will draw over here. So this is my attempt to draw kind of a motor shaft rotating some load. Okay, and we're going to assume that that load is there's some sort of rotational friction. Okay, so let me label this figure. V is going to be our applied voltage. There's a resistance, there's an inductance, there's a so-called back EMF. The voltage produces a torque, tau. Okay, that will cause the load to rotate, which will change its position, angular position, which I'll call theta of t. The load has some inertia, which I'll call J. And like I said, maybe there's some rotational friction, and that's B. Okay, the damping coefficient. Okay, and so you would have seen in other courses that there are so-called motor equations which couple the electrical part, this part, to the mechanical part. I won't go through them all, but in this case, the torque is, roughly speaking, proportional to the current in the circuit. Okay, and the back EMF is proportional to the angular velocity. Okay, so that's not I dot, that's just lowercase I. So let me just try to make that clear. All right. Okay, so you go through your usual modeling of the circuit, the mechanical part, you use the motor equations to couple the two subsystems, and you will end up with a certain model. Now, I won't write down the model, but I'll just mention that it's common when you're controlling a DC motor to assume that the quote-unquote electrical time constant is much smaller than the mechanical time constant. And roughly speaking, what that means is the dynamics of the electrical system are faster than the mechanical of the mechanical subsystem. So it is common to assume that the quote-unquote electrical time constant, which is the ratio L over R, is much smaller than the mechanical time constant, which in this case is J over B. Okay? And so if you make that assumption, what you can do is you can just basically simplify the model of this DC motor a little bit. And so this leads to the model. J times theta double dot, so inertia times acceleration, angular acceleration, is given by, or equals. Sorry, I wanted to use k tau here, not ki. K tau, ke over r times theta dot plus k tau over r times V, the applied voltage. Let's call this constant A1 times J. Call this constant B0 times J. And then take Laplace transforms. So take LTs with 0 initial conditions. And what do you get? You get that S squared theta of S, so remember time derivative is multiplied by S, is equal to A1, negative A1, S times theta of S plus B0 V of S. Rearrange so that you get the input V and the output theta. And so you get the transfer function model. Okay. And so we have our transfer function. And that is the transfer function from the applied voltage on the motor to the position of the motor shaft, theta. Okay? You could also get the transfer function from the voltage, V, to the angular velocity. Remember that in the Laplace domain, multiplying by S is taking the derivative. So if I just multiply that transfer function by S, I'll get the transfer function from V to theta dot. So the TF from voltage to angular velocity theta dot is right, omega is usually the symbol for angular velocity, so I'll use capital omega for its Laplace transform, and you get the simple first order system like so. What are the symbols with circles around them? Oh, capital theta. Sure. So this is my attempt at a capital theta. Okay. So capital theta for the Laplace transform of lowercase theta, right? Okay, so transfer functions. So you've seen them before, you've worked with them before. I want to review now a definition of some terminology which will come up in this course. Okay, so it may seem a little bit dry, but I like to give the definition because at least we're all on the same page. And this is, again, a definition from the notes, so if you don't want to write it down, you don't have to, but let's review it. we're going to say that a transfer function is real rational. So a transfer function, g of s, is real. So this is a three-part definition. So this is part I. Real rational. If it's the ratio of polynomials. In other words, if it's a rational function. If it is the ratio of polynomials with real coefficients. Right? And so it's basically the type of transfer function that you're probably most used to. And what that would look like is the following. Where the AIs and the BIs are real numbers. Okay? So most of the systems we encounter are rational, or have the transfer functions of this form, but there are important examples that do not, right? And so one would be a time delay. A time delay in the Laplace domain is e, so the exponent, to the power of negative s times the time delay. That's an irrational function, so it's not a rational transfer function. If you ever worked with partial differential equations, so for example, transmission lines in power systems, if you model them of infinite length, you end up with irrational transfer functions, okay? But most of the systems that you're going to encounter will have transfer functions of this form. Okay, we're going to say that G is proper if the limit, as s goes to infinity, of G of s exists. In other words, you get some complex number. Okay? Now, if G happens to be rational, it simply means that m, the degree of the numerator, is less than or equal to the degree of the denominator. So if G is rational, we're saying that n is greater than or equal to m. Okay, but the definition 2, which is not in the square brackets, applies to both rational and irrational transfer functions. 3, G is strictly proper if, when you take the limit as s gets large, you get 0. Another way, if G happens to be rational, it means that n, the degree of the denominator, is strictly greater than the degree of the numerator. Okay. Okay, so in this course, I will use terms like rational transfer functions, proper, strictly proper, and the reason I go over the definition is so that we all know what that means. Okay? Another definition, and this is a definition of poles and zeros. So I'm going to give the definition, kind of a general definition, which applies well to rational and irrational transfer functions, and then we'll talk about the rational case. So we're going to say that a complex number P is a pole of G of s if the limit as s approaches P of G of s equals infinity of the let's say the magnitude to be a bit simpler. Okay, That's what a pole is. I'm going to say that a complex number, Z, is a 0 of G of S if the limit as S approaches Z of G of S equals 0. Okay? So poles and zeros. Poles is where the G blows up. So if you imagine if you were plotting the value of G on the S plane, the pole is where you, literally like a tent pole, right? You're pushing it up to infinity around that point. And then the 0, if you're applying the magnitude, is the place where it goes, it touches, if you're drawing a 3D plot. Okay, so that's a general definition, but if G is rational, and its numerator and denominator are coprime, so what does it mean for two polynomials to be coprime? It means they have no common roots, right? So we're saying that if G is rational, it's the ratio of polynomials. And furthermore, there are no common roots between the numerator and the denominator, so coprime. Then poles of G equals roots of denominator and the zeros of G are the roots of the numerator. Right? And so that'll be our most common case, right? Where the poles and zeros are just roots of a certain polynomial. Okay, let's go back to our DC motor. The transfer function from voltage to position was given by G of S equal to B0 over S plus A1. And so this system has two poles. So notice that the numerator, so it's rational, ratio of polynomials. The numerator and denominator do not have any common roots, so they're coprime. In this case, then, the poles are the roots of the denominator. The question is, what is G to be rational? So a transfer function G of S is real. Let's just, okay, ignore the word real for now. Is rational if it's the ratio of polynomials. So it has this form. So let me just do an aside here. So aside, G equals 1 over S plus 1, rational. G equals e to the negative st, irrational. G equals 1 over hyperbolic cosine of the square root of s, irrational. Okay? So your most common case is where it's the ratio of polynomials. Okay? And so this is what we see typically when you start with the differential equation, linear differential equation. This you've seen because it's the time delay. If you have a time delay, like you're doing control over a network, and there's a delay in information coming back and forth, you would have a delay. Oh, so real rational simply means that the coefficients of the polynomials are real numbers. So this is the real part. So the fact that the coefficients come from the real numbers. I'll just mention that this is the transfer function of a transmission line in power systems. Okay, so in this case, poles at s equal to 0 and negative a1 and zeros, none. Okay. So we got 5 minutes. We'll do the next section. Bounded input, bounded output. stability. Certainly something you've seen before. So the definition, I mean, you can look in the notes for what it means for a signal to be bounded, but basically the idea is that a system is BEBO stable, bounded input, bounded output stable, if every bounded input produces a bounded output. So BEBO there is abbreviation for bounded input, bounded output. Stable if every bounded input produces a bounded output. Okay, and I want to emphasize the word every. Okay, so let's do a little mini example. Linear time invariant system, it's an integrator. If the input is u of t, is cos of t, that's a bounded input, right? Cos is it's a number between plus and minus 1 for all values of t. Then y of t equals sine of t, which is bounded. So that particular bounded input produced a bounded output. On the other hand, if u of t equals the step, then y of t is the ramp, unbounded. Right? Integration of a step gives you a ramp. So this system is not BEBO stable, and we couldn't make that conclusion. We couldn't say that it was stable just because we picked a particular input and it happened to be bounded. That is not enough to say that the system is BEBO stable, because it turns out that if you pick a different input, which is bounded, you end up getting an unbounded output. So not BEBO stable. Since every bounded input has to produce a bounded output. Okay. Now, how do we test for bounded input, bounded output stability? You've seen this before. I'll remind you. So I'll just state it as a theorem. But basically, as you know, it comes down to the poles of the transfer function. So theorem 233. So assume G is strictly proper. Rational. Okay, so that means that it's a ratio of polynomials, and the numerator of the numerator polynomial has degree strictly less than a denominator. The following are equivalent. So the first statement is that G is BEBO stable. Okay, that is equivalent to saying that its impulse response is absolutely integrable. And the impulse response is the Laplace inverse of the transfer function, of course. Is absolutely integrable. And by that I mean that if I take the integral from 0 to infinity of the absolute value of the impulse response, I get some number. And I know I'm over time. I'll just write down the third one and we'll stop there. 3, every pole of G has a negative real part. Okay? So those are all equivalent statements, meaning 1 implies 2, 2 implies 3, 3 implies 1. Of course, the one that we're going to use is the last one. This is the statement, this is the test we're generally going to use for BIBO stability. Okay? I'll do some little examples next class, but for now we'll stop there. Sorry for going over a little bit. I'll hang around for a couple of seconds or a couple of minutes to see if there are any questions. Okay? Have a good week. The question is about, should we be able to get through problem set 1 after the completion of chapter 2? Yes, absolutely. You should be able to do parts of chapter 1, or problem set 1 already. Probably by Wednesday you should have the material to be able to do all of the problem set. It will also be the subject of the tutorial on Friday.